Okay, this video is going to talk about our very last distribution, which we're going to do 2 different tests using, and then we will be done. So this is all about chi-squared. So the chi-squared distribution, if you know anything about Greek letters, I think chi looks something like this. So we're talking about the Greek letter chi. And the thing that's different about this is that this is a non-symmetric distribution. So the other 2 distributions that we've been dealing with have been the normal distribution and the t-distribution. And those 2 are both symmetric. So the kind of new thing about this is that when you look at a picture of a chi-squared, and I'm probably going to do a terrible job, but it's something that looks sort of like this. So chi-squareds will look something like this. It changes. There is also a degrees of freedom with chi-squared, just like there was with the t, and that changes based on what kind of test you're running, but it's based kind of on your sample size and sort of the number of categories that you're dealing with. And we'll talk about the different distributions and how to use that. So if you look, there's a chi-squared table in the appendix, and you can kind of look at that and see it. It kind of runs very similar to a t-table. So we'll be using that as we start talking about how to calculate p-values for the test that we'll run with chi-squared. So we'll do 2 sections in this chapter 11. We'll do 11.1 and 11.2. And there are 2 different ways to use chi-squared. One is to do test of independence. And the second is to do goodness of fit test. So if you ever if you ever want to use chi-squared, it's going to be for one of these 2 reasons for this class. So we have normal and t-distribution we use to test means and proportions. We use those for that. And we do that for our class. We're just doing one of those. You can also do 2 means and 2 proportions. We didn't have time to do that in our class, but that is chapter 9 in your book if you wanted to kind of look at an example of that. We're going to skip that. But then chi-squared will do stuff about tests for independence, so if 2 variables are independent, which we talked about in the probability section, and then also goodness of fit test. This video is going to focus on the first one of these, and I will make another video that will focus on the second one later this week. So we are just going to do an example so you can kind of see what what the test for independence is all about. So this is section 11.1, and this is a test for independence. So if you remember back in the probability section, we would talk about if 2 events were independent or not. And there was a probability, like a way to calculate that with probabilities. And sometimes that's really hard to do with the data that you're given. It's hard to exactly tell if 2 things are independent. You may not be able to calculate P of A intersects B. I think you had to check that the P of A intersects B is equal to P of A times P of B to show that 2 things were independent, but you may not be able to calculate all of those things. And so how could you test if 2 variables were independent or not? And that's what the chi-squared test can do for us. So the first step, and this is still a 6-step process, so your first step is still to write your hypotheses. Your hypotheses in this test is always something about the 2 factors are independent, that's your null, or the 2 factors are not independent. So that's how you actually write it in words. So we're going to look at number 13 today, and we're going to look at 13 as our way to go through an example. So number 13 in the book talks about it's generally believed that children brought up in stable families tend to do well in school. And to verify such a belief, a social scientist examined 290 randomly selected students' records in a public high school and noted each student's family structure and academic status 4 years after entering high school. The data were sorted into a 2x3 contingency table with 2 factors. Factor 1 is either graduated or didn't graduate, and factor 2 is either no parent, 1 parent, and 2 parents. The results are given in the table provided, which I'll draw for you all in a minute. And they want us to test at the 1% level of significance whether there is sufficient evidence in the data to conclude that family structure matters in school performance of the student. So, our null hypothesis is that family life and grad rates, or grad status, let's say, are independent. That is always our null hypothesis in these independent tests. So we're always going to assume they are independent. That's the better assumption, is to assume that 2 variables are independent unless we find some data that says maybe they aren't independent. So that's your alternative, is that family life and grad status are not independent. So this will always be your two hypotheses for a test for independence. So anytime you're doing an independence test, it's going to be R independent, R not independent. This one always goes with HA, this one always goes with H0. So make sure that's all you have to write. That's this. If you have an independence test on the exam, on the final, then you just have to write this hypothesis, and you'll automatically get the points. You just have to change what your factors are based on what your problem is saying. What are the two things they're trying to decide if they're independent or not? So that's our first thing. Remember, independent means they don't have any relationship and one doesn't have any effect on the other. And then dependent or not independent is the alternative, and that means that one of those things is affecting the other and vice versa. So in this case, we're testing to see if family life and grad status are actually dependent on each other, right? If there's an actual sort of structure there that actually matters. So that's your first step. So that's always going to be your first step in a chi-squared independence test. Your next step is to check conditions. And the condition you need to check is first you're assuming that the factors are independent. So you want to go into the test assuming they're independent. That's your first sort of thing you check. And you just check that by checking that you believe it for now. And then second, you check that all the observed values are greater than 5. Okay. So in your table, the observed values are the things given in the problem. So given in your table. So just make sure all the values in your table are at least 5. So there'll be a table shown in all these different categories. Just make sure you have 5 in each category. That's your big thing that you're wanting to check. So those are the first two things to check, and we will do that once I draw this table here in a minute. And then once you check those two things, then you know you're going to use chi-squared. So those are your sort of checks of conditions. The first one is not really anything to check. You're just going to go ahead and state that you're assuming the factors are independent. And the second is that everything that you get are all greater than 5. The next thing to do is to calculate a test statistic. And so this is a complicated process for chi-squared. It takes a little while. So the first thing we're going to do is draw the table that comes from the book, because we're going to use that table to calculate a lot of things. So we have no parent, we have one parent, or we have two parents. So those are kind of the different categories for family structure. And then we have either they graduated or they did not graduate. So those were all the categories given in the problem. And again, given in the problem, this was 18, this was 101, this was 70, 31, 44, and 26. So you can make a quick note over here. All of these observed, these are your observed, are greater than 5. And these are often written as an O. So your observed are everything in white. I'm going to write all the next things in yellow so that we can keep track of the two things. So observed are O's, and we have all those in our table, and they're all greater than 5. This is given to us in the problem. The next thing we need to do is calculate your E's. And E. E is equal your row times your column divided by your sample size for each row times your column divided by n for each block. So we're going to do that for this one, this one, this one, this one, this one, and this one. So first of all, note, if you remembered the problem, I read it a little while ago and I read it kind of quickly, but n is 290, so that's our total number of students sampled. That was given in the problem, and you can add all these numbers up and get 290. The other thing we need is the total of each row and column. So you can come across here and get 49. This one is 145, 96. And then we need these columns here, 189 and 101. So those are the numbers we're going to use for this row times column divided by n. So we're going to calculate that E number for each of these 6 blocks, right? One for each of the different blocks. So for this block, we're going to take row, which is 49. So I'm going to talk about this block here first. So I'm going to come down here. And that's going to be 49 times 189, which is the 49 is the row, 189 is the column, and I'm going to divide that by n, which is 290. And if I do all that, I get 31.93. So this becomes 31.93. I'm going to do that same thing for every block. So I'll do one more. Let's say I do this one. That's going to be 49 times 101 and divided by 290. And that gives me 17.07. So we're going to go across this whole table and do that same process. You take the row number times the column number and divide by n. So we'll do it over here. We get 94.5. If you want to try one, feel free and then check your work with me. 50.5. 33.43, and 62.57. So these orange and these white numbers, these two numbers are the numbers we're going to use to calculate our test statistic. So calculating the test statistic is a lot longer of a process than it was in our Z or T test. This is just the beginning of the process. And we're going to have to come back to these numbers quite a bit, so feel free to stop the video and rewind and look at this picture or copy this down as you go forward so you can kind of see what we're going to do. We actually need to calculate the chi-squared test statistic. So we write this as chi-squared. This is capital chi-squared. It looks more like an X. And what it is, it's the sum of the observed minus the expected squared divided by the actual expected, and that's across all the boxes. So if you go back to those boxes and start listing, we're going to have 6 pieces. There were 6 boxes. So it's going to be something plus something plus something plus something plus something plus something equals. So we're going to have to calculate all of those fractions. So if we start out in the very first top box, that's going to be 18 minus 31.93. We're going to square that and we're going to divide by the expected, which are your e's. That's the second number in the problem. Similar, you can go 31 minus 17.07, divide by 17.07. Don't forget to square this. You'll do this for 101 minus 94.5. You'll square it, divide by 94.5. You'll do this for 44 and 50.5. You'll square it, divide by 50.5. And keep doing this. This one's going to be 62.57, and this one is a 33.43. So you have all that stuff. You do all that, calculate it all out, and if I typed all this into a calculator, 21.2784 is my test statistic that I get in step 3. So this is the key formula to know. I think it'll go on your formula sheet, but you have to recognize that O will always stand for the observed, that what was given in your problem, and E is the expected that you calculated based on the thing that we just did in the previous line. Row times column divided by n, and you're going to calculate that for each of your boxes. You're going to sum across all your boxes, that special formula, O minus E squared divided by E, add all that stuff up, and you're going to get your test statistic O chi-squared. So that's step 3. Step 4 is now going to be to calculate a p-value. And now we're going to use chi-squared, and degrees of freedom will always be row minus 1 times column minus 1. So kind of counting how many rows, how many columns there are, and then sort of doing a subtraction. So we had 2 rows here, or 3. I guess we had 3 rows, and we had 2 columns. So if you multiply this out, we get 3. No, not 3. 3 minus 1 is 2, so we get 2, right, times 1 is 2. So we get 2 as our degrees of freedom. So that's the chi-squared table part that we'll use, because you'll see the first thing you have to decide is what degrees of freedom you want. So that's what we'll use when we're calculating our chi-squared p-value. Degrees of freedom is 2. Okay, so I have my chi-squared table pulled up from the appendix in the book. And I'm going to use this. It's the right-tailed area. And for test of independence, we're always going to look at the right-tailed area. So as we calculate our p-value, it is going to be the probability that chi-squared is bigger than whatever number we got, which in this case was 21.2784. So it's always going to be greater than for this test. There's no question of trying to do less than or whatever, it's always greater than. That's the thing you're testing, and that should make sense because all the values you get will be positive, so you're always going to get a positive outcome because you're squaring everything. So you're always going to want to go greater as opposed to less than. Less than normally means negative, but everything for chi-squared will always be a positive number, so we're always going to do a greater than test, and that's exactly what the table shows. So if you go to the table, you get a 2, and you're going across, and you see a whole bunch of numbers. If you go across the table, the last two numbers are 9.210 and then 10.597. So above here, we get 0.01, and this is 0.005. So hopefully it's clear that our test statistic is actually out here somewhere. And again, chi-squared, we're not going to be able to get an exact p-value, but we can certainly say that our p-value, notice the p-values are getting smaller. These are your p-values up here. These are the probabilities. This is the area under the curve, which is also your probability. Notice that those are getting smaller. So our p-value is certainly going to be smaller than 0.005 because our test statistic of 21.2784 is way out here. So we're going to get a really tiny p-value. And that's how you can calculate your p-value from the chi-square table. It'll be similar to the t-distribution. You're sometimes going to get things in between two numbers, and other times you're just going to be so far off the chart that you're just going to go less than or greater than. So next up, now that we have our p-value, step 5, we decide that this is certainly, our p-value is certainly less than 0.01, which was our alpha. I believe this problem said to do the test at 1%. So that would be 1%. And if we have a p-value that's less than alpha, that tells us we reject H0. So this is all just the same as our testing stuff that we did in the last section. The only new part is the chi-squared p-value calculation and the test statistic calculation. Everything else is very similar to what we did before. So the last thing I need to do is just write a sentence about our conclusion for this test. So that's all we have to do, and we'll be done with this test. Step 6. Here's our conclusion. So we have a p-value, rejected H0. So we definitely will say that there is sufficient statistical evidence to conclude that family structure matters in school performance of students. So that's our conclusion because we rejected H0, that they were not related, they were independent. We went with the alternative, which was that we had enough evidence to believe that, and that was that there was actually a relationship. They were dependent upon each other, and so that's why we have sufficient or significant statistical evidence to conclude that family structure does matter in school performance of students.